Since we're going to use a lot of radicals and do a lot of operations on radicals in this unit, we're going to do a little review here. We're going to start with the product property of radicals because we're going to use that when we want to simplify radicals. So the product property of radicals says for any real number, and then it says a greater than or equal to 0, b greater than or equal to 0. That's just saying that these numbers have to be positive real numbers. And of course, the root that we're taking has to be a positive integer. If I'm taking the nth root of a and I'm multiplying it by that same root of b, then I know that's equivalent to taking the nth root of a times b. So I can combine those two real number integers under the radical instead of doing each radical separately. So let's look at how this applies to this radical here. All right, we want to think about what is the largest perfect square that the number 12 has in it, and we know that's 4. So we're going to break that down to 4 times 3, and because of the product property of radicals, then we know that the square root of 12 equals the square root of 4 times 3, which is the square root of 4 times the square root of 3. It's actually using that product property in reverse. And then we just simplify the square root of 4. We know that's 2. We can't simplify the square root of 3, so we have to leave it that way. And that is how we simplify radicals. So let's take a look at this next one. Negative 3, there's nothing we can do there, but let's think about 75. What is the largest perfect square we have in 75? Well, that would be 25, because 75 is 25 times 3. So then we know that we can split that up by doing kind of the reverse of what the product property up there says. So that would be negative 3 times the square root of 25 times the square root of 3. Simplify the square root of 25. We know that's 5. Square root of 3 can't simplify. So then when I multiply these two here, I end up with negative 15 times the square root of 3. Okay, number 3 here. All right, looks like we're going to use the product property the way it's written this time. I know that I can do this. All right, since 6 and 12 are both positive integers, I know that I can combine those under that radical. That gives me the square root of 72. And then I have to think, what is the largest perfect square in 72? I happen to know that's 36, but if you don't know what the largest perfect square is, that's a factor of the number that's under your radical, then I know 72 is divisible by 2, so just start dividing by 2. If you have an even number under there and you don't know what the largest perfect square is, just start dividing by 2 and then 4. And finally, you'll get to something. And what we know is that 72 is 36 times 2. So then we know that this is the square root of 36 times the square root of 2. So that's going to simplify to 6 times the square root of 2. Okay, so that's the product property of radicals. Now we got the quotient property of radicals. So again, if we've got real numbers a and b and they're both positive, then we know that we can take the nth root of a divided by the nth root of b, and we can combine it to be the nth root of a divided by b. So in other words, we can take the quotient of a divided by b, and then we can take the nth root, the square root, cube root, whatever we're doing there. So let's see how that plays out in example number 4 here. All right, I want to go ahead and just apply my quotient property. So instead of taking the square root of 50, dividing it by the square root of 2, I'm going to combine that, take the quotient, and then take the square root of it. Well, that's really nice because 50 divided by 2 is 25, and I know the square root of 25 is 5. Okay, how about number 5? Well, I don't have a radical in the numerator, so I'm not really applying the quotient property here, but what do I know? Well, I know this isn't simplified because I cannot leave a radical in the denominator. So what we learned a long time ago is that when we have a radical in the denominator, we have to do what's called rationalize that, and we're going to multiply numerator and denominator by what that denominator is. And why can we do that? Because this number here just equals 1, so it's okay if I multiply a number by 1. Now when I multiply fractions, I multiply numerators, so 2 times the square root of 3 will be in the numerator. Square root of 3 times the square root of 3 just gives me 3, because that would be the square root of 9, right, by the product property, and we know that's 3, and none of that can be simplified anymore, so that is going to be my final answer. Okay, how about number 6 here? Well, I'm going to have to rationalize it again, but I don't need to multiply by the whole denominator this time. I just need to multiply by the radical. So I'm going to multiply top and bottom by the square root of 5. So on the top I'll have 7 times the square root of 5. On the bottom I'll have 2 times square root of 5 times the square root of 5. It's going to be 5. So when I put all that together, I'll have 7 times the square root of 5 over 10. Be very careful you don't think you can do anything with this 5 and this 10 here, because remember the 5 is under the radical, so you cannot simplify that in any way with the denominator there. Okay, I put one for you to practice here. So I want you to pause this video and I want you to write this one down, number 7, on a sheet of paper, work it out, and then come back here and I'll talk you through it. Okay, hopefully you realize that if I take this 12 over 4 here, that I can simplify that to 3. So I just really split these up. And then I've got my square root of 18 over the square root of 6. I can apply my quotient property that says I can take the quotient first and then take the square root of it. So when I put all that together using my properties, I end up with 3 times the square root of 3. Now let's see, could we have done this another way? Sure we could. Let's look at this. We could have simplified the numerator. We could have said this is 12 times square root of 18. That would be 9 times 2, right? Still got our same denominator, over 4 times the square root of 6. Then I would take the square root of 9 here. That would give me 3. Then 12 times 3 is 36 times the square root of 2, and that's divided by 4 times the square root of 6. But oh my goodness, then I got other work to do here. 36 over 4 is 9, but then I've got times the square root of 2 over the square root of 6. Then I'd have to rationalize that. Ooh, that's definitely not the way I want to do that. I would come up with the same answer eventually, but this is definitely going to be our preferred method of solving that problem. And sometimes it just takes a feel for working a lot of these problems before you can realize up front what the best way is going to be to solve them. Okay, how about adding and subtracting radicals? You must have like radicals in order to add or subtract them. Well, what does that mean? What are like radicals? How about this? What if I had 3 times the square root of 3 plus 2 times the square root of 3? Those would be like radicals because both of my numbers have the square root of 3. I got the same root, I got the same number under the radical. So how about the square root of x minus 2 times the square root of x? Those would be like radicals, right? Because I got the square root of x here, and I also have that in this number. How about non-examples? Well, how about if I had 3 times the square root of 3 plus 4? I couldn't combine those because I don't have a radical here, right? So those would not be like radicals. I couldn't, let's say this, what if I had the square root of x plus the square root of 2x? Those would not be like radicals because this number inside is not the same. Okay, so let's see how we use this in some actual problems. What do we got here? 9 times the square root of 3 plus 2 times the square root of 3. Definitely like radicals because both numbers have a coefficient, and then we have the same radical, same root, which is 2, same radicand, which is 3 under there. So what you can do is think about this. What if you had 9x plus 2x? I know that's 11x, right? I can think of this the same way. What you could do here is you could factor out the x. That would give you 9 plus 2, which would give you your x times 11. So you could think of this in the same way. I could factor out that square root of 3. I'd have 9 plus 2, so kind of doing the distributive property in reverse. That would give me the square root of 3 times 11. And of course, we'd want to put that in standard form with our radical at the end. So that would be 11 times the square root of 3. All right, how about these two? Number 9, we got the square root of 8 plus the square root of 2. Definitely not like radicals, but hey, we can simplify this one, right? And then maybe they will be like radicals. What's the square root of 8? Well, that's 4 times 2 plus the square root of 2. All right, if I take the square root of 4 here, that's going to give me 2, and then I still got the square root of 2 under there, and then I got the square root of 2 here. So hey, I do have like radicals, and I have 2 of these plus 1 of these, so that's going to give me 3 of these square roots of 2. Think about it. If it was 2x plus 1x, I know I'd have 3x. So if it helps you, maybe think of your radical as a variable. Okay, how about number 10? Ooh, you know what? Let's get rid of our parentheses first. So let's say minus 5, negative 5 minus the square root of 18. And then I'm going to distribute this negative here. So that'll be minus 6 minus the square root of 50. Now I know I can combine the negative 5 and the negative 6. That's negative 11. So I'm going to put that out front here. And then I got minus the square root of 18 minus the square root of 50. So now I got to work on simplifying these two radicals. So let's see here. I know the largest perfect square in 18 is 9, so that's going to be 9 times 2. Largest perfect square in 50 is going to be 25. That's 25 times 2. So now, let's see what we got here. Negative 11. If I take the square root of 9, that'll give me 3 with the square root of 2 left over. If I take the square root of 25, that'll give me 5 with the square root of 2 left over. So then I can combine these two. Can't combine either one of them with the negative 11 because there's no radical with the negative 11. So that's going to give me negative 11, and I got negative 3 minus 5, so that's minus 8 times the square root of 2. And that's going to be my final answer right there. Okay, so just like before, I got one for you here to practice. Pause here, write this down on your paper, see what you get for your most simplified answer. Okay, so at first we can see they're not like radicals, so what we got to do is simplify these radicals, and maybe they'll turn out to be like radicals. Largest perfect square in 63 is 9. 63 is 9 times 7. Largest perfect square in 24 is 4. So then when I take the square root of 9, I get 3. So I'm just going to bring this 3 down. 3 times 3 gives me 9 here. Got the square root of 7 left over. And then when I take the square root of 4 here, I get 2. Okay, this 2 just comes on down. Square root of 6 stays under because I can't simplify that. Multiply these two guys together, I get 4. I got the square root of 6 left. And here I got the square root of 7. I got the square root of 6. So clearly they're not like radicals. So I can't combine these two. This is my final simplified answer. So I hope that was helpful. If you need more work on radicals, please check out Khan Academy. I'm sure you can find some other great examples to work on there.